Hello, everyone. So this is the first workshop that we're not doing live. Um, I sort of um, realized that we weren't going fast enough, I don't think, to get through everything that I wanted to by the time classes start. And just like having to try and go to pace that people there live can follow along with was a big part of that. So from now on, we're just gonna, and most people were watching the videos anyway, so it's all good. So not doing anything live, so I can just sort of zoom through this, and um, I'm not expected to go to pace where you can follow along live. You can pause the video or whatever. Um, but yeah, other than that, I'm gonna try. I think another reason we were going slow is like I just love C++, um, and I sort of get sidetracked all the time just talking about random things about it and like why I did things a certain way. I'm gonna try and keep that to a minimum. I'm still gonna explain like architectural decisions, and obviously like stuff directly related to game engine programming, but general C++ concepts I'll try and cut down on that because I think I'm starting to repeat myself, and also at this point like I don't know, it should really be expected that you have a firm grasp of the basics. Okay, so that being said, I'll briefly go over just sort of what we ended up with last time because it was a bit confusing. It was kind of a mess. But we just have here in our main file this chunk of code, which generates a 100 by 100 grid of tiles, all of the same sprite. So, and we're storing it all in one render object. So if we run here, we'll just see that we have this. We can resize our window and the proportions of the image remain constant, which is good. At least I think it's good. I like that. It's easy enough to disable if you don't like it, which is perfectly understandable because it's sort of like hacking around a system that exists, you know, for a reason in OpenGL. But either way, I'm going to leave it because I like it. I like maintaining the. I like my images to look like what they look like. So this time we're going to finish off our engine renderer here. So we did a little bit of work on our graphics render. We just added this other draw function that takes in an array of textures instead of just a single texture, and binds them all to separate slots and then draws everything. And I think we actually did manage to finish our renderer. We just aren't using it yet. So this is our engine render. It just sort of wraps a graphics render and has a bunch of neat stuff sort of contained within it. So it handles time for us, and it'll display that time to the like the title of the window. It'll display frames per second information there. It sets our scale for us automatically. It sets the camera for us. Yeah, so the problem we have right now is that we have this 100 by 100 grid of tiles, but we can only see like 20 of them or something. So we need a camera to move around the screen, and so we did part of that setup last time, just sort of condensing a bunch of functionality into the renderer. And today we're going to finish that off. Okay, so first step obviously is to actually use one of these renders. So I'll go ahead and include it here. Graphics/render. And then I'm just going to replace all of our GFX renderer stuff with an engine render. And of course, our engine renderer actually does store a shader. So we don't need this separate shader anymore. Okay, there's that. Then all of this time stuff and the scale stuff, I'll just go ahead and comment that out. Render.clear is the same. Render.render is pretty much the same, just we don't need to pass it any arguments. And then render.draw, we did this a little bit differently. It takes a render object, which is the same, and then a vector of sprites. And then it doesn't take a shader because the render stores a shader. So the vector of sprites, you could have this be just an array of sprite pointers, which would also be fine. I'm not sure why I did it vector here. It doesn't really matter though, as long as you're careful about like when you allocate that vector. As long as you're not doing it too often, you should be fine. But the reason it's sprites in our engine render instead of textures like in our graphics render here is that this is kind of the point of wrapping everything in an engine library. It's like it's another level of abstraction on top of our graphics stuff. So we don't want to use graphics. Like we don't want to make the user use graphics, our graphics library classes directly. They should use the engine wrapper classes for those graphics classes. So we take in an array of sprites here, or a vector of sprites. So I'll go ahead and just create that up here. Standard vector of sprite pointers, call it sprites. And then we are just sort of hard coding a single sprite up here called sprite. So for now, I'll just give it that. And then down here, pass it sprites. And when we run, we should just get exactly the same thing. There you go. But now we can see our FPS displayed up here, which is very nice. You can see what I was saying last time about like the actual like current frames FPS. It's just nonsense. Like I don't know. You can tell how many digits it is, but not much beyond that. And even the average one changes pretty quickly. So something interesting here, just quickly, is obviously this is running very, very fast, and that's because we're not doing a whole lot, right? Like we're rendering all of these stuff. Yes, it's 10,000 different things, but it's all a single draw call. So the GPU is just going to parallelize that, just totally. Like it's a single draw call, as little overhead as possible, and it's just going to draw everything, like all at once. So that's why it's so fast. But you can see if I like move my mouse around, that average FPS starts to drop. And similarly, if I like type, I guess typing doesn't do it. But yeah, moving your mouse around, any sort of like window events are going to slow it down. And that's because the operating system has to like intercept those events and dispatch them to the appropriate place, I guess. And if you resize and stuff, it like stops the thing from running. Like you can see my FPS isn't changing at all. Same if you grab the thing up here. But yeah, that's just useful because you can see like it's not super accurate because it is like averaged over the whole lifetime of our whole program, like since we've started running. So like as you leave it running for longer and longer, the current FPS is going to have a smaller and smaller effect on it. But for our purposes, just like testing stuff quickly, it is very good to see. It's like a very simple benchmarking tool, I guess. You can see like how long different things are taking. Okay, so we do have this camera, it's this set camera thing, and we have set up a simple camera in our game loop here before, but we've never been able to move it, and that's because we don't support input right now. That's not a thing we can do. We don't have a way to handle mouse events and key events. So let's do that, and then we can move our camera around with WASD or the arrow keys, whatever. So the way we're going to do this is, so this might be sort of weird. I'm not sure. Like if you were using a real or making a real game engine, obviously you'd want to support multiple different graphics APIs. And I'm not sure how those deal with input, but in our case, GLFW actually deals with input for us. It's like the windowing library, it's called. So it's like the interface between OpenGL and the operating system. And the operating system receives all the events, and then GLFW receives them from the operating system, and then we can get them from GLFW. So there's a few things we're going to do. We want key events. We want like whether or not a key is pressed. We want mouse movement, mouse button clicking, and then also scroll wheel. So scroll wheel is a little bit weird. We have to set it as a callback, sort of like our window size callback here. I'm not sure why that is. My only guess is that that's how operating systems implement it. But like the other stuff, like key state and mouse button position and key presses, like we can just query directly. But for some reason, scrolling you have to do with a callback. But just before that, like I'm gonna add a really sort of hacky vec2 type here. That's just gonna store 2 floats. It doesn't have to be a math vec2. We don't need to do any operations on it. It's just a way that we can return x and y, because we'll need that for mouse coordinates and also mouse scrolling. Because I guess some mice support horizontal scrolling, where you can like click your scroll wheel left and right. But let's go ahead and set up the scroll callback. glfw set scroll callback. We set that on our window. And the function we pass takes in a window, of course. Window pointer. And then it gives it to us as doubles. But we're not going to use doubles. We usually use floats for everything. Just because that's what it ends up as on the GPU. I mean, you can do like double precision floating point operations on your GPU, but they're slower. So we just use floats for everything. So glfw get window user pointer on our window. We'll cast that to an OpenGL instance pointer because it's just void when we retrieve it. And then we'll have this additional field in our OpenGL instance, just a vec2 called scroll. And then down here, set our scroll equal to x and y as floats, just like that. That's all we need to do. So this callback just, again, it's kind of weird they did it this way, but it just receives the x and y, like, I guess, velocity of your scroll wheel whenever it's scrolled. But one thing that is important to note is that this is not called when you stop scrolling. So if I'm scrolling like up, for example, like this, that might be 0x and -1y. But then when I stop scrolling, this callback won't be called. So we're going to have to reset that manually, just so that our engine doesn't think we're scrolling even though we stopped. But that's pretty simple. Okay, then we'll just add a couple functions here. I'm going to make a few of them private, just as like helper functions. So we'll have isKey here, which will return glfw get key on our window. The key, we've passed it, and we'll check if it's equal to state. So we'll give it like the key code here, so the key that we want to get the state of, and then whichever state we are looking for. So like, is it pressed? Is it released? Whatever. Then we'll also have isMouse, which is basically the same thing, just for mouse buttons instead of keys. Okay. And then we'll have a few public functions here. So like isKey pressed, return isKey, the key code we got, and then glfw underscore press is sort of the macro for that you want to check if it's equal to. I think there's also glfw release, but I won't implement that because it's trivial. So for mouse buttons, we could do a similar thing, like isMouse pressed, and then take in a key code. But really, it's I think it's a lot cleaner to do isMouse left and isMouse right, because those are like the buttons you're most interested in. And if you want to do anything further, like check if the mouse has 3, 4, like extra buttons on the side of it or whatever, you can still use this same function. But I'm just going to do left and right. That's all we'll need. So isMouse glfw mouse button left, and that same glfw press. I'll just copy that and replace left with right. And then we want, the last thing we're going to do is get our cursor. Get cursor pause. So this one also gives, it like returns doubles. and because it has to return multiple values, we just pass it in pointers. But again, we're going to cast everything to floats. Okay. So there we go. Now, in our engine core here, we did like this is good enough. We don't really need to wrap these because we do have an OpenGL instance pointer that's publicly accessible in our engine instance, but I still think it's a lot nicer to just wrap these. It's not that much work. Just so you don't have to call like engine.gl dot whatever. You can just call engine dot is key pressed. So is key pressed. Just like that. And then we'll do mouse left and mouse right. And then for our position, now that we're in our engine, we will actually convert it to a proper vec2. Just so that we can perform operations on it if we want. So we just get this sort of basic graphics library vec2 thing that we define over here that just stores 2 floats. Oh, and I forgot to set my default values. That's not necessary, but just to be thorough. You should set it to 0. So we just get those x and y, and then this looks like weird and redundant, but this, like doing this will actually convert it to a vec2, or I don't know, you might be able to just return this and like the compiler will figure it out. It'll say, okay, it has the same fields, whatever, but I don't know. And then get scroll. So we can actually have like a get scroll function in our engine here, even though really it's passed as a, it's not passed, but scroll state is like updated through a callback. But remember, we're like storing a vec2 of it in our instance, so we can just have a function here that just gets that. And I'll do the same thing here, just convert it to a math vec2. Okay, so like I was saying, like scroll that callback doesn't get called when you stop scrolling, so we're gonna have to do that manually. And I'll just do that in our engine renderer, our clear method up here, just at the end, because this runs at the start of every frame. So we will do, we have our engine pointer, GL scroll, and we'll just set that to 0 ourselves, just like that. Actually, no, we can't do that in clear. The reason we can't do that in clear is that clear runs at the start of every frame, and our oh, where is it? Here it is. Our render function, which runs at the end of every frame, is where we actually get our events, so GLFW poll events. Now, I'm not sure if this affects scroll callbacks, like this, you know, GLFW set scroll callback. I'm not sure if that's like actually a direct callback where when Windows receives a mouse scroll event, it will call this function, or if GLFW puts that into a sort of queue and then just goes through the queue and resolves everything when you call GLFW poll events. I'm not sure. So I think we'll actually put our clear at the end here, just above our GLFW poll events thing. Wait, we We should do this in the engine render and render. Here we go. Like that. So now, basically, this will like, because this runs at the end. So if we have a scroll state, we can like use it in our game loop, like our logic there. And then at the end of the frame, we clear it, and then this will reset it to whatever its GLFW has received, if not. And again, I don't know about that. I should have tested that beforehand if it how the callbacks work exactly. But yeah, that should work. And we're not gonna like we might use that for debugging stuff, but we're not gonna use it. Okay, so now that we've got like all this key state stuff we can do, we can actually set up somewhat of a proper camera. So we'll just have a vec2 like before. Then I'll have like a cam speed. It's just a multiplier there. And we can get, so we want to do all this before our draw function. So we'll move our camera if necessary, if we're pressing any keys, and then we'll update render's camera. Because remember, our render.setCamera thing, it just sets uniforms in the shader. So we need to do that before we draw stuff. Otherwise, our camera will like lag a frame behind everything that's being drawn. Which in this case won't actually matter, but eventually, once we do like dynamic things, like stuff that moves around the screen, we'll have an actual, like a proper camera class that sort of has a dynamic object as its target, in quotes, like the thing it's trying to follow. And every frame will just update that, and it will calculate an offset based on its target's position that will draw its target right in the middle of the screen. And that's where the like order of updating this stuff becomes important, because if you move your camera, then move your dynamics, and then draw everything, the camera's target may have moved after the camera offset was calculated, and so that'll be like, it'll look jittery. But for now, it doesn't matter, but we should still do it properly. So we'll move camera and then update the shader stuff. So we'll just have a float called offset here. And I have this syntax I like to use. Just like subtracting the key states. I think it's very clean, be intuitive. So this basically just says, it just handles WASD the way you'd expect. You can figure that out. And now we want smooth movement. So we're going to use our render.get frame delta, which we haven't used before, I don't think, but we have set it up now where frame delta is just the difference in milliseconds between the start of the current frame and the start of the last frame. So it like attempts to account for the any sort of inherent latency going on between frames to give you smooth movement. So we will multiply our offset by our cam speed, and then by our render.get frame delta. Now, our frame delta is, as I said, in milliseconds. But that's, I don't know. I sort of like use milliseconds and seconds various ways throughout my program, but when I'm thinking about movement, it's a lot easier for me to think in terms of seconds, because I can just look at this speed and say, okay, that means I'm moving 100 pixels per second, instead of saying, okay, that's 100 over, there's 1,000 milliseconds in a second, so that's what, 0.1 pixels per millisecond. That's just kind of weird. It's a lot more natural to think of it in terms of seconds. And so we could account for that here just by dividing by 1,000. But actually, I'm going to go ahead and do that in our function here, just because I think every time I use this, I'm going to be dividing it by 1,000. So we'll just take the stored millisecond value and return it in seconds. And that way we don't have to worry about it. Okay, so for now, we'll just go ahead and add that offset to our camera vector, and then I'll call it down here, update the camera, render.set camera, and let's see what we get. Very nice. So we can move around, just sort of verify here that we have, 100 tiles or whatever. This is pretty slow, so I'm not going to go all the way up. But you can see that our grid thing actually is working, and it's all laid out right next to each other. So well, actually, I should start again. One thing you may have noticed is that if I move diagonally here, and it's kind of hard to see because this is pretty slow. So let me turn the speed up a bit. I'll go 250. When I move diagonally, I move faster. So this is just normally just like single axis movement, but when I move diagonally, it's clearly much faster. And this makes sense. This is just the Pythagorean theorem, because our logic here just says, okay, based on the states of A and D, set my X, and based on the states of S and W, set my Y. And there's no actual like relationship between these two. So if you're pressing A or D and S or W, then you'll move by 1 unit or 1 times the speed in both axes, which is, square root of 2 times the intended speed. So we'll just add some logic here to check against that. So we can use if not math is 0 offset.x, and math is 0 offset.y. So if we're moving in both axes, then we will divide our offset by the square root of 2 to give us that unit, like magnitude diagonal vector, and that's what we get. So that's just a simple trick there. If you were doing like a more complex thing, like you'd have linear algebra, like if you want your character to properly rotate and not just have like this sort of weird 8-directional grid movement, then you'd have to, it'd be a bit more involved with like sine and cosine and stuff. But for us, we're always going to be moving at a 45-degree angle because our speed in the x-axis is the same as our speed in the y-axis, so we can just divide by square root of 2 and it'll work fine. Okay, so that's like all we're gonna do, I think, with the renderer for now. And we are getting into the exciting part, I think. We've done a lot of good groundwork, but as I sort of mentioned last time, as you can see by like all of this mess up here, you can't really make a game. Like what we have right now is not a game. It's barely even, like a passable sort of playing field for a game. Even if your game only consisted of like this one grid of things and it was like a super simple single screen, like, I don't know, infinite spawn enemy like type game. This is still a pain. Like this sucks. We cannot have this as our system for storing map data because it's not storing map data. It's like hard coded into the engine. So that's what we're going to do next is map data. And I have a little like spiel here written out just about map data, and more importantly, our rendering pipeline, which is sort of the next big chunk. So rendering pipeline includes map data, which we're going to do now, then lighting after that, which is just like adding, lighting effects within our shaders, which is pretty cool. And then finally, dynamic stuff. So like I was saying with the camera, we'll eventually give that like a dynamic pointer that it'll follow around on the screen. So dynamics are just things that we will be modifying their vertex data directly. So they are actually moving around within the world and not just moving relative to the camera. And these are big things. Like this is kind of tough. Up to now, it's been tough. At least for me, it was very hard to learn all this stuff just because it's a lot of like stuff. Like there's no way around it really. Like you just have to know what to do with all this OpenGL stuff and how it all works. You just have to do it. But now we're getting to the point where there isn't like a correct way to do things. It depends on your game. It's not just stuff that you can look up like, oh, I wonder how I, do this a certain way in OpenGL. It's not that. It's like you have to understand what your goals are in terms of like the types of games you want to make or the type of engine you want to make. And you have to understand what is in your way for like getting to those goals. So right now, our biggest obstacle is we have to hard code all of our map data, and then you have to come up with a system for fixing that. And I love this. This is like my favorite part about game engine stuff. Is I mean, obviously the graphics is cool, and it's I don't know, it's sort of endlessly fascinating to me how quickly all this stuff is drawn. Like you could see there, it's running at like 1600 FPS, which is just insane. Um, but these actual like architectural decisions are, I think, very valuable experience because it doesn't only apply to game engine stuff. Like you could take these sort of high level skills that you have of, um, having an idea, knowing what you need to do to accomplish that idea, and designing some system to accomplish that. That applies to anything basically, not even just programming, but especially programming. Any sort of career where you want to be a software engineer, someone writing software, designing software. This I think hopefully will be valuable experience. So I'm really excited to get into it. But let's talk about map data now. So as I've said many times, this is an issue. We need to fix this. That's why we're doing map data. You basically couldn't create a 2D game, hard coding everything. 3D stuff, I don't even want to think about. And so we need some other way to store our map data, not in code, especially. That's the big part because, like right now, it's fine because our engine is small. It compiles quickly. That's like what 3 seconds to recompile everything. But eventually, even our little engine here will get bigger, and we're using a precompiled header, but we'll probably have, I don't know, 3-4 times this amount of files in our source folder here, and it'll just be a pain to recompile. So we need some external way to store map data, similar to how we're using bitmaps. Even though like we didn't design the file format for bitmaps, that is like data external to our engine that we are then importing into our engine and using with our sprites. And that's essentially what we want to do for map data, except we have to come up with the files now. So let's think about like what our maps need to have. And unfortunately, like that's the first big question, right? Is okay, so I'm designing this sort of map like file type. Well, what do my maps need to have? It is basically entirely dependent on what kind of games you want to make, like what you want your engine to be designed to do. For us, we're only doing 2D, so that does simplify it a bit, I guess. But it still heavily depends on the application you want. So for something like this, obviously this little demo I have here, this would be like sort of a 2D, like top-down Zelda-style RPG, where it's like a world made of a grid of tiles, essentially. But if you want to make like a fighting game, that'll have sort of these huge background textures that take up like the whole screen, and they like have parallax and they scroll relative to each other. If you want to make like an old like arcade style shooter, like I don't know, like Galaga or Asteroids is a big one. You'd want sort of like arbitrary level geometry. It is like a single screen, but I don't know. So, but the point is that it depends on your application, and you can't. Well, you can do them all, but not cleanly. And so, like, I don't know. We could write like some super complicated map system that can handle all of this stuff, but it would be lower level than we need it to be, and that we want it to be, because based on the survey results that I took like before starting this, people weren't really interested in like designing our own file types. That's why we use bitmaps for textures, and we're just going to do a simple text-based map thing. We're just going to store them in .txt files, where again, like really, if you were really making a game engine, you would have some optimized like binary file format for whatever type of game you are making, and you would have like an editor that generates those binary files for you. But for us, we're just going to do it all through text, so it'll be super easy. Now, I would like to point out that all of those like example games I mentioned, like fighting game, RPG, all that, our graphics library is totally capable of doing all that. Like that's not the issue here. The issue here is how how quickly we want to be able to create our games, and for our purposes, we want to be we want to be able to do it really fast. So we'll just make it like a very simple thing that's super easy to use. But inevitably, there you do lose some level of control over what the maps actually are. But I've tried to set it up in a way that you can, if you want to make some type of map stuff that isn't like necessarily supported by the type we're going to write, you will be able to edit the sort of map file type very easily. So we aren't interested in like any particular type of game for this. We're just like general 2D stuff kind of. So we're going to go for our maps in the direction of just arbitrary level geometry. That might be kind of misleading because we're still doing everything with only rectangles. That simplifies a lot. But arbitrary level geometry meaning like it's not like a RPG where everything has to be a strict grid of tiles. Nothing like that. You can put tiles wherever you want at whatever coordinates. They can overlap, all that stuff. So this is sort of just the most general case for like what is feasible for us to write. And it'll give you guys like a good amount of freedom when you're creating your games for the game jam. So we sort of have an idea of like what we want our maps to contain now, and that's a good start, right? Like you need to know what your goal is before you start writing code. Minutes of planning can save you hours of programming. But really, our issue becomes now: how do we split this data up? Like we're gonna have, arbitrary level geometry, so we could have a tile, anywhere we want. And should each of these tiles, like they're not really inherently connected, should they all be drawn separately? That's no. Like the answer there is straight up no. We talked about this a little bit last time, but our renderer in our renderer class here, we're calling GL draw elements. This is what's called a draw call, and sort of behind the scenes in whatever OpenGL implementation your graphics drivers have, this does a lot more than just straight up drawing stuff. Like it's basically a command that gets put into a queue of all other OpenGL commands, and then I don't know like the timing of it exactly, but once per frame maybe. Like it might be this GLFW swap buffers that sort of does it, or it might be an asynchronous thing, like synced to your GPU. But this puts it into a queue of commands, and there's a lot of overhead there because not only is it not going directly to our GPU and saying, okay, use this shader, draw this stuff, go. It's like masked behind this OpenGL implementation, and then it has to wait to be processed. So there is a lot of overhead there. So minimizing draw calls is definitely one of our goals. So that's like the most important thing. That's really what we're going to be considering when I say like we need to know how to split the data up. And the best way to minimize draw calls, I found, like the simplest way, is to use a process called batch rendering, which is like basically essential. If you're doing anything 3D, it is literally essential. But if you're only doing 2D stuff, you could probably get away with not batching anything, but it would be very, very inefficient, very messy, and again, like even though this is small, I want to show you guys like the correct way to do stuff. So we need to take our map data, which is arbitrary. We don't know what it is. It could have 100 different texture files, and we need to figure out how to batch that we need to like separate it out into groups that can be drawn all at the same time, all with a single draw call here. Um, and this isn't as much of a process as it sounds. Like all batch rendering means is that we write our shaders in a way, and we create our vertex data in such a way that we can draw a whole bunch of stuff with a single draw call. The biggest bottleneck I've found is the number of texture slots. That's sort of like the most restrictive factor here, because our vertex data can basically be as big as we want it to be. I mean, obviously there is some physical limit, but we are never going to hit that with 2D stuff, so we don't have to worry about that at all. Same for index data. But textures, we have at most 32 of those to use at any given time. So our draw calls are really going to be limited by that, where every single sprite that we load in, every single bitmap, will be stored as a single texture, and we can only draw 32 like objects that use 32 of those. All right, my headset died, but it's back now. So what I was saying is, like, the only thing we're constrained by really is the number of texture slots we have. We can only draw things that use 32 unique textures at any given time. And there are ways to optimize this far beyond what we're doing. Like our textures are pretty small. They're very small actually. Like the bitmaps I made was like 40 by 80 pixels or something. It's just tiny. And like we could have this sort of like system that at runtime it gets all of our textures and combines them into much larger textures, because modern GPUs can support up to like 4096 by 4096 pixel textures. And so we can take a bunch of like different 40 by 80 textures or whatever and sort of cram them in there, and then just sample from that much larger texture in our vertex data using texture offsets. But this isn't something I've even ever done, like a system to do that. That seems like a pretty complicated algorithm to me, is like fitting a bunch of these arbitrarily sized rectangles into another like bigger rectangle in an efficient way to maximize space saved. And I've never needed to do that to have an efficient 2D render. So we're just going to skip out on that. But really, like, that's a system that you maybe should have eventually if you have a much bigger game. But for our purposes, each texture is just a single bitmap. So yeah, like everything we just talked about is a rendering pipeline. It's like part of one. It's taking data from disk from our map files, loading them into our engine, turning those map files into vertex data, and splitting it all up in ways that it can be efficiently drawn. So that's like a good start. When we after map stuff and lighting stuff, we'll do dynamic stuff, and that's like a pretty big addition to our rendering pipeline. It's honestly more complicated, but for now, this is like what we need, right? If our goal is just to take this sort of hard-coded grid and turn it into a text file and get the same result, this is what we need. And the whole rendering pipeline thing, it might be the most difficult part of all this. Collision handling is kind of a beast as well. Not just like the actual math to resolve collisions is pretty simple, but setting up a system to do that efficiently is very involved. But we'll get there when we get there. But even just this, even the rendering pipeline, it takes a lot of code and a lot of planning went into it, and you need a good amount of experience, like thinking about time efficiency, especially. That's like the main consideration. I sort of touched on that last time when I was talking about like why we don't dynamically allocate in our render.draw function here, like why we store our texture buffer and texture frames as part of our renders object, like as fields of our render. But if it hasn't been made clear yet, time efficiency is basically all that matters. Space, we don't care about. We can assume it's infinite, because to us it is. Like we're never going to even come close to hitting the upper bound on space. So time is basically the only consideration we need to make when designing this stuff. So even though, like I just said, it takes a lot of planning and experience and stuff, I don't think I would consider myself to have a lot of experience. I have done this before in several different ways, so like I know what I'm doing to some degree, and I'm capable of writing something that works and is fast. But like I was saying about like the sort of that algorithm to like dynamically combine multiple small textures into bigger textures, that's like something that um, is not only out of scope for this, but is out of my realm of knowledge. So yeah, like I'm not an expert. If you have questions, I'll try and answer them. But there is a possibility that I won't be able to. But on that note, I was watching this talk on YouTube from GDC, Game Developer Conference or something, um, by a developer at id Software, who was he like worked on the team or was the head of a team responsible for porting some Doom game, I don't know, from OpenGL, the graphics library we're using, to Vulkan. Vulkan is another graphics API, sort of open source, multi-platform. That is, I think it's maintained by the same group that maintains OpenGL, but it is much lower level. And so basically my point is that this guy is an expert. Like he has this experience. And he said something that I thought it wasn't only funny, but it's like it sort of hit home. It said, how do you build a renderer? Well, it's easy. First, you get a black screen, then you get a colored triangle, then you get a textured cube, and then you write everything else. And that's where we are right now. We've got, we had our sort of black screen at first, or blue screen. Then we got some colored triangles, some colored rectangles, all good, all good. Now we've got some textured squares on our screen. And we're at sort of the threshold now where we've got to start writing everything else. And what he means by that is sort of what I was saying. There's like no right way to do this. You have to come up. You have to figure out how to do it. If obviously if you like once you have a direction and you run into problems, you can look those up on Stack Overflow, Wikipedia, just like you do everything else. But you're not going to find anywhere unless you're just copying like directly from some tutorial. You're not going to find like guides on this on like how to structure some arbitrary game engine. It's our job to come up with that. Um, and so with all that said, let's actually get started on writing the everything else part of it. So the first thing we're going to do is in our graphics folder here, we're going to make a new class called Sprite Bank, because when we are loading from files that have like an arbitrary number of different textures that we need to use, we need some way to manage those. So ours is just going to be super, super simple. All we're going to have is an unordered map of strings, so the file path, to a sprite pointer. And this is something that would change like depending on the format of your map data. Like for my the personal game engine I work on, it is pretty much exclusively designed to do like Zelda style 2D grid based games. And so I have like my own map file format and everything, and to support map serialization, like saving stuff out to maps that is designed in the editor, you can't just have a map of like file paths to sprite pointers. You have to give everything like an index. It's almost like a SQL database. It's like an associative sort of thing. There are lots of IDs going around just so that you can actually save it out in a somewhat compressed way. So our constructor here doesn't need to take anything. We'll just initialize it with an empty map. Then of course I'll do the I will delete the copy and move constructors here. We will have a destructor that we'll write in a minute, and we'll just have two functions here, put and get. Both will take in a path, but put will take in frames and time as well. Now we will create a C++ file. We'll actually include sprite. Okay, so we have our destructor. I'll do that in a minute. And then we have put and get. So put is going to check if our sprite bank contains a sprite with this description. And if it does, it'll just return it. Otherwise, it'll add that sprite to the sprite bank and then return it. And get will just get from our map. So you can use that if you know something exists, and our put function will use it as well. So let's write get first. It's very simple. We'll just do a find for our path on our map. And if it exists, or if it doesn't exist, we will just return null pointer. Otherwise, we'll return the sprite that is stored at that path. And then in our put, we'll call get on the given path. If it exists, so if we already have a sprite at that path, we will return the existing one. Otherwise, we'll have to create a new one. Path frames and time. Put it into our map at the given path, and then return it. So one thing you may notice about here is that we're just mapping strings, straight up file path. So you can't have, in a sprite bank, multiple like copies of a file. Well, obviously that's the point, but you can't have you can't load test and say, okay, it has 2 frames and the time is 1,000. You can have that, but then you can't also have test with 2 frames and time as 2,000. You can't do that because all we're checking for is file path. And for us, that's good enough. But if you wanted to have it where you can't, or sorry, you can have multiple like copies of the same file path as long as it doesn't have the same frames and time, then you could implement that as well. You would have like you would just have to store not only the file path here, but also information about frames and time, and that would be it. But we're just keeping it super simple. Okay, so our sprite bank destructor is, I mean, it is simple, but it's sort of an important concept. When our sprite bank is destroyed, it's going to go through its map and delete all of the sprite pointers. Because you can see here, it dynamically allocates sprites here, so we need to delete those at the end. But this is like an important thing to realize is how this is designed. We don't have this like interface that's like void add, and then the user gives it a sprite pointer. We don't have that. And then it's up to the user to delete it. We have this sort of ownership idea where any sprite that is added to our sprite bank is owned by the sprite bank, and therefore it is up to the sprite bank to delete that sprite when it's done with it. And in our case, when it's done with it just means when the sprite bank itself is deleted. And this is an important thing. Obviously, in this case, it's very, very simple, but when we get into doing like our collision stuff, like that's a much bigger process and it's a lot more interconnected. So just be thinking about that. Okay, so that's actually all we need for our sprite bank. Super, super simple. I'm going to create a new folder here called world, and this will just store everything about like map data. And then another very simple header file called tile.h. So tile is just going to be like a single element that is drawn on our map. It's like a single rectangle, basically. So it has a sprite, some sprite pointer. It has a position. And it has I'm going to go ahead and add these, but we won't be using them till quite a bit later. It has a layer, so we'll be able to specify like whether or not it's in the foreground or background, basically. And then rigid, which will be like whether or not it has a hitbox, basically, whether or not other things can pass right through it. And we'll just default that to false. Okay, so that's all we needed for tile. And now we're going to sort of like design our map loading pipeline from the bottom up. So we could go top down and say, okay, I'm going to start with my map. I know this has to load from a file and turn it into stuff. And I thought about doing it that way. This was very hard to like structure in an intuitive way, like a good layout, a good order to teach this stuff in. I couldn't really find one that I was happy with, but ultimately I decided to start from the ground up, where we're going to start with like the lowest unit of our sort of map loading pipeline, which is what I was talking about, batching things together. So drawing, like separating things out into groups of 32 unique textures so they can be drawn all at the same time. So that's what we're going to start with. And we'll sort of work our way up. We'll start with this called a sprite group, and then a chunk, and then a map, and then eventually a world. Sprite group.h, and then we'll also have sprite group.c++. Let's go ahead and create that. Okay, so this is going to store, each sprite group is going to consist of a single render object. So a vertex array and index buffer. And then we'll have a vector of sprites called imSprites. Now this doesn't have to be a vector because we're not going to be like resizing it. I just made it a vector because it makes writing the constructor a little bit easier. So all we're going to take in is a map of sprite pointers to a vector of tiles. So this may seem a bit confusing, but the unordered map type and like unordered set, they use a, I'm just going to gloss over this. If you don't know, you can look into it yourself, but they use a hashing function by default called standard hash. And this is something that you can like override and define for your own custom types, which is very useful. Or, I mean, basically, you can just pass unordered map a hashing function that you want it to use. But we're not going to get into that. I don't really know how to write hashing functions. That's like a whole nother area of computer science. So we're just going to use the default one. And the default one has specializations for pointer, the pointer type, because a pointer is just a number. And so it can hash that essentially the same as a number. So that's the reason that this works. So we're just mapping sprite pointers to all of the tiles that use that sprite. Because remember, our tile class stores, it has a sprite, the sprite that is used to draw that tile. So that's all that is. I'll go ahead and delete everything here. And this is actually the point where like deleting these things becomes very, very helpful in this sort of map pipeline. So in our destructor, we'll just delete our render object. That's going to be dynamically allocated because we don't have a default constructor for it, and there's not really a reason to do that. So it just makes it way easier, just having it be a pointer. We'll have a draw function that draws the whole thing all at once. And this sort of helper function, static function that just returns get max texture units. Okay. So our constructor is pretty complicated, but I think we can get through it. I'll just initialize my render object to null pointer, as I was saying, and that's all we need to do. So we have this map of unique sprites to tile data, that tiles that use those sprites. And we have to generate vertex data for all of these tiles. We want all of the tiles to be contained within our single render object. So we sort of need to just go through each one and like figure out which sprite it's going to use. Because remember, in our vertex data, if I go to our shader real quick, the way we tell it which sprite to draw is, oh yeah, we use this texture index thing. Texture index. So texture chords tells it where to sample from the texture, but texture index tells it actually which bound texture to use to sample from. And that's just a number. It's just an integer basically. So we have to convert this sort of map of sprite pointers and data containing those pointers. We have to enumerate it essentially. So we'll get our max here, get max sprite count. And then if our data.size is greater than max, size returns the number of map entries we have here. And a map entry is just a pair of a sprite pointer and a vector of tiles. So it's not concerned about the length of the vectors, just the number of pairs that you have basically. And if we have more pairs than we do the number of sprite count that we support, that means we have more sprites than we support. So we can't possibly bind all those for a single draw call, which is an error. So cannot create a sprite group with this many sprites. Must be at most our max count. Okay. So we need to know the total number of tiles that we have. So we're going to have to go through our whole map here. So for every pair, we'll just get the second component of that pair, which is a vector, and add the size of that vector to our tile count. So that'll give us the total number of tiles we're trying to draw. And then we can, using that, determine how many floats we need to draw. So that's going to be S floats per vertex times S vertices per quad times tile count. And then we'll create a float array of that size to store everything and then delete it down here. Okay, so now we need to go through our whole map. And this has to happen in 2 stages. First, we need to go through every sprite. And we will add that to our list of sprites. And then I'll just get some constants down here to help. Let's get the width and height of our sprite. Oh, I didn't include graphics/sprite. There we go. So sprite width and sprite height. And then now we have to loop through every tile in the vector associated with our current sprite. And then for each tile, we have to generate 4 vertices. vertices per quad. Oh, some other stuff I forgot to add up here is because of the way we're like looping through this, like with this like range-based thing, we're not actually using an index. I'll just keep track of like offset stuff outside of it because we kind of have to. So offset will be the like index, the next available index in our vertex array, essentially. And index, our float index here, will be the number of the sprite that we're on. This is the text index that we'll be sending and putting in our vertex data. So vertex offset, the start of any given vertex, is the offset of the current quad, plus the number of vertices you've processed for this quad so far, times the number of floats in each vertex. And then we have 5 floats per vertex, so we'll set all of those like this. Okay, we need to define this. So what we're going to do here, I'll sort of separate these out. We have our XY pair, then we have our ST pair, and then we have our index. So this is just going to be index. Simple. Our ST, like I was saying, for this simple implementation, each texture on our GPU will be a whole sprite. So these will just be like combinations of 0 and 1, basically. And so we'll define another like thing array in our engine core file here to actually store that. So we have this index offsets 1, but we want a float 1. I'll call this corner points. You could call it like texture chords, but it's going to be used for more than that. But yeah, so counterclockwise from the bottom left, we have 0, 0, 1, 0, 1, 1, and 0, 1. So that's our corner points. We can use that in here, both to set the texture indices, S and T, as well as the position. So our tile actually, remember, it stores a position. So it has a vector. It has tile.pos.x and .y. But for each coordinate, for each vertex, those have to have different coordinates because we want our sprite to have width. We don't just want it to be a single point. And so for like the bottom left coordinate, that can just be our position. We'll say bottom left is like the local origin of a sprite. But then the bottom right needs to be at the x coordinate of the origin plus the width of the sprite. And then the y remains the same. And then for top right, both y and x have to get their like corner point over here added to it. So that's what we're going to do here. I'll just take these same sort of things here. 0 for x and 1 for y, because that's the order we stored it in. X, Y, X, Y, X, Y, X, Y. And then multiply by the dimensions of our sprite, like that. And it gives you this error here. Well, it's not an error, but it's like a warning, at least Visual Studio does. Buffer overrun, writable size is float count times 4, but 8 byte. I've not been able to figure out what this is. My guess is that it's thinking that because the size of our array is float count, that depends on tile count, and it sees that tile count is initialized to 0, so it says, okay, so this could be 0, so you're like overwriting. I don't know, but this isn't actually an issue. It's just the like compiler being dumb. Okay, so that's actually the vertex data, and then so this runs once for each tile, and then once we're done processing a tile, we need to increment the offset by the number of floats that we just wrote. And then once we're done processing each sprite, which is this loop, so all this runs once for each sprite, we will increment our index. So our map, obviously it's unordered, it just comes in some random order, but we sort of enumerate that in this way by looping through each sprite first and then incrementing the index for the next sprite. And then once we're done, we will just create a render object with our data. So float count, our vertices, 221 is the format. And then indices per quad, vertices per quad, and index offsets, like that. And then of course we are later deleting this in our destructor. So that's our sprite group constructor done. It's a little complicated. Hopefully you were able to sort of understand all this. And when I push this code to GitHub, I'll comment everything out, so you can go through and read that if you're still confused. Hopefully that'll clear it up. But our draw function here is very simple. I'll just copy this. All we need to do is call render.draw with our render object and our vector of sprites. And that's it, just a single line. So we've done all the processing here, and then when we draw, we just need to use the vertex object or the render object we created. We store each sprite in the map that we get in our vector here, and then just pass that on to the render. So that might actually be all we're doing with sprite group. I'm not sure. We might end up coming back later. I can't remember. But the sort of next stage is the chunk. This is like the next group up. So basically the way our maps are going to work, and if this seems like somewhat nonsensical or at least non-optimal, that's because it totally is. Again, like I had to sort of write a system here for the most general case. So it's going to have some weird decisions in there. But the way our maps work, and I'll sort of draw this out a little bit. Say we have this rectangle, and this is our whole map. Then we might have some data over here, some tiles over here, some other tiles in like a different group over here. Like you get the idea. It's just like our whole map contains this, but we can sort of separate it into these smaller little groups. And each of these groups is a chunk. So all the individual data within that chunk will be what's passed to our sprite group here as this unordered map of data. But the job of each chunk, I suppose, is to determine how to split up all the data it contains into those sprite groups. So we have like the overall map, and then we have chunks. So each of these is a chunk. So our map's job is to split its data up into chunks, and then our chunk's job is to, partition its data up into sprite groups that can all be drawn at the same time. And the way we're going to do it is like within a map, no overlap between chunks can exist. So that way we only have to draw one chunk at a time. And the way we'll determine which chunk to draw will be like based on the position of the player. So whichever chunk the player is in, that's the one we'll actually process. But yeah, that's like the basic hierarchy. The map contains chunks, and each chunk contains sprite groups. So the sprite group's job is to split it up into like generate data for our GPU, and the chunk's job is to generate data for our sprite groups. So we'll add that, chunk.h, and chunk.cpp. And this is going to be a bit more involved. There's quite a bit of logic. So I'm going to go ahead and do something kind of confusing. but it'll make sense when we get to our map. I'm going to create this object called a chunk constructor. And this just stores all the information we need to create a chunk without actually creating that chunk. And we'll come back to this later and sort of keep adding stuff to it. So starting out, obviously, we will just have a vec2 that is the position, and then we'll have a vector not of tiles, but of sprite groups. Then our constructor will just take in a chunk constructor object. I don't know why I keep writing chunks. Then delete this stuff. And then we don't need a destructor. And then our draw method is just as simple as the last one. Just going to go through each group and draw it. So really the only complexity that exists in our chunk is the constructor. So I think I'm actually going to just like do this the whole way through because I don't want to stop in the middle. And now that this isn't live, I'm not like exactly constrained by time. But yeah, this like video might be a little longer. Okay, so we'll just copy the position from our constructor into our chunk in this list here. And now we actually have to start splitting it up. So our sprite group takes an unordered map from sprite pointers to vectors of tiles. So that's what we need to send it to, or send to it. So we have this constructor here, which just has a vector of tiles. And again, each of those tiles stores which sprite it uses. So we technically have all the data we need. We just need to chunk it into a format that our sprite group can then take in. So we'll have a vector of unordered maps of sprite pointers to vectors of tiles called groups. So this is just a list of these unordered maps here that our sprite groups take in, and when we're done processing, we'll just go through this vector and create a new sprite group for every unordered map within the vector. And then we'll also do something here that isn't necessary, but it is like a good performance improvement. I'll explain that in a minute, but that's what that indices map is, even though it may seem unnecessary. So we're going through each tile in our constructor's vector of tiles, and we'll get the sprite from the current tile. Now, we have this list of groups here, and we need to figure out which group it should go in. Because each of these groups contains multiple sprites, and so we need to figure out, which unordered map the current tile's sprite goes within. And we could do like a for loop here where we loop through every unordered map in our groups vector and check if it contains the current sprite as a key. That's bad, like for bigger maps. For it, I don't know, it probably won't matter, but like theoretically, that's slow because you have to loop, like the checking whether or not a map has something as a key in unordered map is order 1, assuming you have a good hash, which you can. It's like amortized order 1. But checking a vector, it's not sorted. You have to go through each element in the vector. And so if you have a lot of groups, that becomes order in, which is bad. So instead, we will just cache. We'll have this separate unordered map of sprite pointers to a uint. So we'll map sprite pointers, so like things that the tiles use to draw themselves, to the index of the unordered map that contains that sprite within our vector here. So we'll check if we have that first of all. So if indices.find sprite, and then if we don't have that, so if we haven't done anything with current sprite yet, so this is like a new sprite, we haven't added it to any groups, we need to find a group to put it in. Create these two variables here. And then we will loop through all of our existing groups. And if the group at our current index, the size of that is less than the maximum number of sprites our group can contain, we will set found equal to true, and then break, and then our uint I here will retain whichever index it was at when we broke from the loop. So that'll have the correct index into our groups array here to add our current sprite to. If it's not found though, so if this check never returned true, that means that none of the existing sprite groups have any room for another sprite. So we need to create a new sprite group. So I have unordered map temp. And then into that, we will insert our sprite and then an empty vector of tiles. And then we will add this, or we could do in place back as well. We will add this map to our vector of groups. And then we'll set I equal to groups.back, groups.size -1, 0 indexed. So this will give us the last valid index in our groups array, which is correct because we've just added this to the back of the array. So it'll be the last element now. Okay, so at this point, we've either found an existing group to put our current sprite in, and we know the index of that group, or we've created a new group and put our sprite in it, and we know the index of that group as well. So actually, we should take this out, or no, we can leave that there. I don't know. There might be a cleaner way to write this. So if not found, we create a new group and add it. Otherwise, we have an index stored in I of an existing group to add it to. So we'll just do that. The same thing, adding current sprite and an empty vector of tiles. Okay, so now it's guaranteed that our current sprite has a place to be within our groups array. Then we will set index equal to I. Index is this one we defined up here. And we will actually cache this index. Indices.insert our current sprite and our index, so we can find it next time in constant time. Okay, so all of that was if cached equals indices.in. So if this is a new sprite that we haven't seen before. Otherwise, if we have seen this sprite before, our index is just going to be equal to the result of this find operation. So that returns a pair of sprite and uint. We want the uint, so we get the second element. Now, we've inserted the sprite. We have a place for our sprite, but we haven't actually inserted the tile yet. So index at this point represents the group within our vector here to insert our tile into. So groups.atIndex.at, because that returns a map, and then .@sprite, the current sprite. So groups.atIndex gives us one of these, and then and then that map.atSprite gives us a vector of tiles to actually add to. So vector.pushback tile, or in placeback, it doesn't matter. And there we go. So this is pretty complicated. I don't know. It's not that big of a function. It's probably about the same size as our sprite group, but it is somewhat like you have to like think about how it works. I guess it's kind of complicated. So then once we've separated all of our data out into groups, we've gone through this whole for loop of going through all tiles in the vector that we took into the constructor. Then we have a complete list of groups, and we can create and add a group to our actual list now. And there we go. So our constructor just takes in a bunch of tile data, not sorted in any way, sorts it, creates sprite groups from it, which then in turn create vertex data so it can actually be drawn. And then we just have a draw function here to draw all groups all at the same time. Yeah, so that didn't actually take as long as I was thinking. Hopefully this part made sense. Again, when I post this to GitHub today, I'll like go through and comment everything more or less line by line, just so that it's very clear what's going on. Because even to me, like I wrote this, and like if I'm just skimming this, like what is this? This is a ton of like complicated stuff happening. And if you don't have comments to explain it, it's kind of just hard to read. So it's good to write comments, even if it's just for yourself. But yeah, so hopefully you enjoyed this. I think, as I've said, like this sort of architectural stuff is very interesting to me. I like designing these systems. And we actually made a lot of progress today, more than I was expecting. Next time we'll just do our map class, which isn't like as architecturally difficult. Like it doesn't have all this logic of like splitting stuff up like this, but it is a lot of code. And we're going to use some cool C++ tricks in there to make it very clean and easy to write, and also easy for you to extend if you want to add additional functionality to our map files. So yeah, hopefully you enjoyed this, and I will have a new video posted sometime this week, at least by Saturday, but probably earlier than that. So I'll see you then.